In today's lecture, we examine materials in architecture not merely as construction components, but as strategic elements that shape environmental performance, urban identity, and disaster resilience. The title Urban Morphology and Hazard Exposure highlights the critical relationship between the physical form of cities and the materials that constitute them. Urban morphology refers to the spatial structure, patterns, density, and physical organization of urban environments. Every street, facade, pavement, and public space contributes to this morphology. Materials are fundamental in defining this structure because they determine texture, scale, reflectivity, durability, and environmental response. When cities are exposed to hazards such as earthquakes, floods, extreme heat, or climate-related risks, the performance of materials becomes a decisive factor. A material that performs well aesthetically but fails structurally during seismic activity cannot be considered sustainable. Similarly, materials that intensify urban heat island effects compromise environmental resilience. Therefore, materials must be evaluated through three interconnected lenses. 1. Environmental performance. 2. Structural and disaster resistance. 3. Urban and cultural continuity. Sustainable cities are not built solely through advanced technologies, but through informed material decisions that integrate ecological intelligence and structural safety into the urban fabric. This lecture is structured around a progressive understanding of material strategies. We begin with life cycle analysis, LCA, which provides a methodological framework for evaluating environmental impact from extraction to disposal. Next, we explore ecological planning and resource management, focusing on climate compatibility and sustainable resource use. We then analyze concrete and cement, addressing their environmental challenges and discussing green alternatives. Following this, we evaluate glass in terms of energy performance and disaster safety. We continue with natural stone and its role in sustainability and cultural continuity. Metallic materials are then discussed in relation to structural efficiency and disaster resilience. We examine material decisions in disaster-prone areas, emphasizing soil conditions and building typologies. Material strategies in large-scale structures are analyzed from economic and durability perspectives. Finally, we conclude with future sustainable construction materials, including smart materials and circular design principles. This structure allows us to move from theoretical frameworks to applied material strategies. By the end of this lecture, students should be able to critically evaluate materials beyond their surface characteristics. You will understand how life cycle analysis quantifies environmental impact and why early-stage design decisions significantly influence carbon emissions. You will be able to compare conventional materials such as reinforced concrete with low-carbon alternatives and evaluate their performance in different contexts. You will analyze the structural behavior of materials under seismic conditions and understand how mass, stiffness, and ductility influence disaster resistance. You will also assess material decisions at urban and infrastructural scales, recognizing how material continuity affects spatial identity and resilience. Ultimately, you will develop a multidisciplinary perspective that connects material science, environmental sustainability, and urban design. Cycle analysis is one of the most powerful tools for assessing sustainability in architecture. It shifts the focus from immediate cost and appearance toward long-term environmental impact. The life cycle of a material consists of several stages. 1. Raw material extraction. 2. Manufacturing and production. 3. Transportation. 4. Construction and installation. 5. Use and maintenance. 6. End-of-life disposal or recycling. At the extraction stage, natural resources are removed from ecosystems. Mining, quarrying, and deforestation can cause habitat destruction and biodiversity loss. These impacts must be accounted for when assessing sustainability. During manufacturing, energy consumption becomes critical. Materials such as cement and steel require high-temperature industrial processes, leading to significant greenhouse gas emissions. Embodied energy refers to the total energy consumed during these processes. Transportation also contributes to carbon emissions. Locally sourced materials generally have lower environmental footprints due to reduced transport distances. The usage stage is often the longest and most complex. A material that requires frequent maintenance or replacement may ultimately consume more resources than a durable alternative. Indoor air quality is also relevant. Materials emitting volatile organic compounds, VOCs, negatively affect user health. The final stage involves disposal or recycling. Circular economy principles encourage reuse and recyclability. Steel and aluminum can be recycled multiple times without significant quality loss, whereas composite materials are often more difficult to separate and reuse. Life cycle analysis therefore transforms material selection into a data-driven, environmentally conscious decision-making process. Material selection does not only affect individual buildings, it shapes entire urban environments. At the urban scale, materials define the identity and continuity of streets. Pavement materials influence pedestrian comfort and orientation. Consistent textures improve legibility and accessibility. Facade materials contribute to visual coherence. When buildings within a district use compatible materials, urban continuity is reinforced. Conversely, abrupt material contrasts may create fragmentation and visual noise. Material choices also influence microclimatic performance. Dark surfaces absorb heat and contribute to urban heat islands, while reflective or permeable materials can mitigate temperature increases. Public spaces such as squares, parks, and pedestrian zones require materials that are durable under heavy usage, non-slip for safety, resistant to weathering, easy to maintain. Local materials strengthen the connection between architecture and geography. They preserve cultural identity and reduce transportation emissions. For example, natural stone used historically in a region often reflects geological conditions and traditional craftsmanship. Urban material strategies therefore integrate environmental performance, cultural continuity, and functional durability. Ecological planning is based on the principle that architecture must coexist harmoniously with natural systems. Material selection in ecological planning prioritizes climate compatibility. For instance, high thermal mass materials stabilize indoor temperatures by absorbing heat during the day and releasing it at night. This reduces energy consumption in hot climates. In cold climates, highly insulated envelopes and advanced glazing systems minimize heat loss. In humid climates, breathable materials prevent moisture accumulation and mold formation. Ecological planning also considers materials as part of natural cycles. Renewable materials such as timber can regenerate if responsibly sourced. Recycled materials reduce demand for virgin resources. Resource management strategies include supporting local production networks, preferring renewable materials, reducing waste generation, designing for longevity. Durability is a core ecological principle. A material that lasts 100 years is often more sustainable than one that requires replacement at every 20 years. Therefore, ecological planning shifts the focus from short-term efficiency toward long-term environmental balance. Concrete is the backbone of modern construction. However, its environmental footprint is significant. Cement production is responsible for approximately 7 to 8% of global carbon dioxide emissions. This high impact is due to two factors: 1. Fuel combustion during kiln heating. 2. Chemical decomposition of limestone during clinker production. Although cement represents only about 10 to 12% of concrete's volume, it accounts for the majority of its carbon emissions. Furthermore, aggregate extraction alters landscapes, and steel reinforcement increases embodied energy. However, concrete also offers advantages: high compressive strength, fire resistance, long service life, structural stability. The challenge lies in balancing structural performance with environmental responsibility. Green concrete strategies include reducing clinker content, using industrial byproducts such as fly ash, incorporating recycled aggregates, developing alternative binders. Sustainability discussions must also consider operational energy. Buildings consume significant energy for heating, cooling, and lighting. Therefore, material strategies must integrate both embodied and operational performance. Concrete's future depends on innovation, regulatory adaptation, and integrated design thinking. In the previous section, we discussed the environmental burden of traditional cement production. At this point, the concept of green concrete emerges as a critical innovation in sustainable construction. Green concrete does not simply mean using less cement, it refers to a comprehensive strategy aimed at reducing embodied carbon while maintaining or even improving structural performance. The fundamental approach involves lowering the clinker ratio in cement mixtures. Clinker production is the most carbon-intensive stage in cement manufacturing. Therefore, reducing clinker content directly reduces CO2 emissions. One widely adopted strategy is the use of supplementary cementitious materials, SCMs. These include fly ash, blast furnace slag, silica fume, and natural pozzolans. These materials are often industrial byproducts, meaning their reuse prevents waste accumulation while reducing the need for virgin cement production. For example, fly ash, a byproduct of coal combustion, can partially replace cement in concrete mixtures. When properly proportioned, it improves long-term durability and reduces permeability. Blast furnace slag enhances resistance to chemical attack, particularly in aggressive environments. Another promising development is limestone calcined clay cement, LC3, which significantly lowers carbon emissions compared to traditional Portland cement. Geopolymer concrete, which uses alternative binders instead of Portland cement, is also gaining attention. However, challenges remain. Green concrete must meet strict structural and regulatory standards. Construction industries tend to be conservative due to safety concerns. Therefore, technological advancement must be accompanied by policy frameworks and industry adaptation. Green concrete represents a transitional step toward decarbonizing the construction sector without compromising structural reliability. Concrete, when used alone, behaves as a brittle material. It performs well under compression but poorly under tension. This limitation is overcome through reinforcement with steel bars, creating reinforced concrete systems. Reinforced concrete combines compressive strength and tensile resistance. In seismic conditions, ductility becomes the key performance indicator. Ductility allows structures to deform under stress rather than collapsing suddenly. However, reinforced concrete systems are heavy. According to Newton's second law, force equals mass multiplied by acceleration. In earthquakes, heavier structures experience larger inertial forces. Therefore, mass plays a critical role in seismic design. The effectiveness of reinforced concrete in disaster resistance depends on proper reinforcement detailing, strong column weak beam design principles, quality control during construction, accurate soil analysis. Soil conditions significantly affect seismic behavior. Soft or liquefiable soils amplify ground motion, increasing structural stress. Modern seismic design philosophy does not aim to prevent all damage. Instead, it aims to prevent collapse and ensure life safety. Controlled damage mechanisms are incorporated to dissipate energy. Thus, concrete's disaster resistance depends not only on material strength but also on structural system design and engineering precision. Glass is one of the most transformative materials in modern architecture. It redefines spatial boundaries by introducing transparency, daylight, and visual continuity. Natural daylight improves psychological comfort, reduces dependence on artificial lighting, and enhances productivity in work environments. Studies show that well-daylit spaces improve cognitive performance and user satisfaction. However, glass is also thermally sensitive. Excessive glazing may lead to overheating in summer and heat loss in winter. Therefore, glass must be integrated strategically rather than applied indiscriminately. Modern glass technologies address these issues through double and triple glazing systems, low emissivity, low E, coatings, solar control coatings, argon or krypton gas fillings. Low E coatings reduce heat transfer while maintaining transparency. Solar control glass reflects infrared radiation, limiting overheating. The concept of the building envelope has evolved from static protection to dynamic performance. Glass facades now integrate shading systems, ventilated cavities, and smart coatings. Thus, glass is no longer merely a visual element, it is an energy-regulating component of the architectural envelope. Despite its advantages, glass remains a brittle material. Improper design may result in dangerous fragmentation during impact or seismic movement. Laminated glass improves safety by bonding multiple glass layers with interlayers. When broken, fragments adhere to the interlayer rather than scattering. Tempered glass increases impact resistance, but shatters into small pieces when broken. Each glass type must be selected according to context and risk level. Facade systems must account for wind loads, seismic drift, thermal expansion, differential movement between structural frame and cladding. Flexible connections are critical. Rigid connections may cause stress concentration and premature failure. Modern facade engineering integrates performance simulation tools to predict stress behavior under multiple scenarios. Therefore, safe glass design requires interdisciplinary coordination between architects, structural engineers, and facade specialists. Natural stone is one of the oldest construction materials in human history. Its durability and compressive strength have allowed historical structures to survive for centuries. Stone offers excellent resistance to environmental factors such as UV radiation, temperature variation, and abrasion. Unlike many synthetic materials, it ages gracefully. Local stone use enhances sustainability by reducing transportation emissions and supporting regional economies. It reflects geological identity and strengthens cultural continuity. Historically, stone symbolized permanence and authority. Contemporary architecture often reinterprets stone through innovative detailing and hybrid systems. However, stone is heavy. Structural support systems must account for weight. In seismic regions, stone is often used as cladding rather than load-bearing material. Stone extraction also affects landscapes. Responsible quarry management is essential to minimize ecological damage. Thus, natural stone represents durability and cultural memory but must be integrated responsibly. From a sustainability perspective, natural stone offers several advantages. First, its longevity reduces the need for replacement. Long service life translates into lower life cycle environmental impact. Second, stone requires minimal maintenance. It does not require painting or chemical treatments. Third, stone production typically involves mechanical processing such as cutting and polishing rather than high-temperature chemical transformation. Compared to cement or ceramics, its embodied energy may be lower. However, transportation distance significantly influences environmental performance. Locally sourced stone is far more sustainable than imported alternatives. Stone also provides thermal mass, contributing to passive climate regulation. Therefore, natural stone demonstrates durability-based sustainability, provided it is sourced and managed responsibly. Metallic materials play a central role in contemporary structural systems. Steel has high tensile and compressive strength, allowing large spans with minimal cross-sections. Its ductile behavior under seismic loads enhances disaster resilience. Aluminum is lighter than steel and highly resistant to corrosion. It is frequently used in facade systems and secondary structures. One of the most significant sustainability advantages of metals is recyclability. Steel and aluminum can be recycled repeatedly without substantial degradation of properties. Prefabrication is another advantage. Metal components can be manufactured off-site, improving quality control and reducing construction waste. However, primary steel production is energy-intensive. Therefore, recycled steel significantly reduces embodied energy. Metal systems are compatible with modular construction, allowing disassembly and reuse. This aligns with circular economy principles. In summary, metals offer structural efficiency, recyclability, and modular adaptability, making them essential in sustainable and resilient architecture. In disaster-prone regions, particularly earthquake zones, metallic materials, especially steel, play a crucial role in structural safety. The key property that makes steel advantageous in seismic design is ductility. Ductility refers to a material's ability to undergo deformation without sudden failure. Unlike brittle materials, ductile materials absorb and dissipate energy during seismic events. During an earthquake, buildings are subjected to lateral forces. Steel frames are capable of redistributing stresses through plastic deformation. This controlled flexibility reduces the risk of catastrophic collapse. Another important aspect is structural weight. Compared to reinforced concrete systems, steel structures are lighter. Reduced mass results in lower inertial forces during seismic acceleration. Lightweight steel systems, such as cold-formed steel profiles, are increasingly used in low to mid-rise structures. Their advantages include reduced structural load, faster construction, factory-controlled precision, dry assembly methods. Additionally, steel systems are ideal for post-disaster scenarios. Temporary housing units, emergency response centers, and modular health facilities can be rapidly deployed using prefabricated metal components. The modular nature of steel construction also supports scalability. Units can be expanded, relocated, or reconfigured as needed. However, steel is not without limitations. Fire resistance must be addressed through protective coatings or encasement. Corrosion control is also essential in humid or coastal environments. Ultimately, metallic systems represent a balance between structural efficiency, recyclability, and adaptability, key attributes for resilient architecture. Material selection in disaster-prone areas must be informed by both environmental and geotechnical conditions. Soil characteristics are fundamental. Bearing capacity, settlement potential, and liquefaction risk determine structural strategy. In soft soil regions, heavy structures may experience amplified seismic motion. Building height is another critical factor. As height increases, lateral forces and structural complexity increase. In high-risk seismic zones, low-rise or mid-rise typologies are often considered safer and more manageable. Material lightness becomes a strategic advantage. Lightweight materials reduce seismic load and improve structural control. Examples include wood-based systems, lightweight steel frames, composite panels. Wood, in particular, has gained renewed interest in earthquake engineering due to its favorable strength-to-weight ratio and natural flexibility. Composite materials combine structural efficiency with reduced mass. They are often used in facade systems and prefabricated panels. Flood-prone areas require different material strategies. Materials must resist moisture, corrosion, and biological degradation. Elevated construction systems may be necessary. Therefore, disaster-responsive material decisions must integrate hazard type, soil conditions, building scale, maintenance capacity. Resilience is context-specific and cannot rely on universal material solutions. Large-scale structures such as mass housing, public buildings, and infrastructure projects require systematic material strategies. In mass housing, repeatability and cost control are essential. Standardized building elements allow efficient production and reduce waste. Durability is particularly important in housing projects. Frequent maintenance or replacement increases long-term environmental and economic costs. Public buildings, such as schools, hospitals, and governmental facilities, must combine structural safety with symbolic representation. Materials in public buildings often convey permanence, reliability, and institutional identity. Infrastructure projects, including bridges, transportation hubs, and water systems, demand maximum durability and resistance to environmental stresses. Materials must withstand mechanical wear, chemical exposure, and climatic variation. In large-scale projects, material strategy must balance structural performance, economic feasibility, environmental impact, long service life. Integrated planning ensures that large developments contribute positively to urban sustainability rather than increasing ecological burden. The future of architecture depends on innovation in materials and design philosophy. Smart materials are capable of responding dynamically to environmental changes. For example, thermochromic materials change color based on temperature. Phase-change materials store and release thermal energy. Self-healing concrete repairs microcracks through chemical reactions. These materials improve energy efficiency and extend lifespan. Circular design represents another transformative concept. Traditional construction follows a linear model: extract, produce, use, dispose. Circular design replaces this with reuse, recycling, and regeneration. In circular construction, materials are selected for disassembly. Components are modular and reusable. Waste is treated as a resource. Next-generation composite materials combine high strength with low weight. Examples include natural fiber reinforced composites, bio-based resin systems, recycled plastic mineral panels. These materials aim to reduce resource consumption while maintaining structural integrity. Digital fabrication technologies also influence material innovation. Parametric design allows precise material optimization, minimizing waste. Future sustainable architecture will not rely on a single material solution. Instead, it will integrate adaptive systems, circular strategies, and interdisciplinary research. Throughout this lecture, we have examined materials from environmental, structural, and urban perspectives. Material selection is not only a technical decision but also an ethical and ecological responsibility. The environmental footprint of construction is directly linked to material production and life cycle performance. Life cycle analysis provides a comprehensive framework for evaluating environmental impact beyond immediate cost considerations. Concrete, while structurally reliable, presents significant carbon challenges. Green alternatives aim to reduce emissions without compromising strength. Glass enhances daylight and transparency but requires careful thermal and safety design. Natural stone demonstrates durability and cultural continuity, especially when locally sourced. Metallic materials offer structural efficiency, recyclability, and disaster resilience. Material decisions in disaster-prone areas must be context-sensitive, considering soil conditions, building scale, and hazard type. Large-scale structures require integrated material strategies balancing cost, durability, and environmental responsibility. The future of sustainable construction lies in smart materials, circular design, modular systems, and innovation. The key takeaway is that sustainable and disaster-resilient cities begin with conscious, data-driven, and context-aware material decisions.